This is an EL320-240-36 electroluminescent military and aerospace display. It's currently playing back Bad Apple at 60 FPS being streamed over USB with PWM pixel dimming to get those gray levels, which actually require updating the display at 120 FPS. Funnily enough, this display does not have a frame buffer at all. This means that all data needs to be constantly streamed into the display. Otherwise, it will go blank if you go for a few milliseconds without supplying new data. I'm not the first one to get one of these displays up and running. Here, for example, is a similar one being driven on Hackaday, or this one on a random blog I found. But what sets my driver apart from the above is that mine costs about $5 to $6 in BOM cost and uses commonly available parts, excluding the display of course. Today's protagonist is the rp2040 and its incredible PIO peripheral. I want this video to be both a project log on how I got the display working, and an overview of how one builds something quite high performance using the Pico SDK, to hopefully give you a starting point to start trying things yourself. So let's start from the beginning. Why the rp2040 if there are cheaper or more powerful or better MCUs out there? You would be correct. The rp2040 on its own is not a very good MCU. It's a pretty low power Cortex M0, it has no FPU, and it only runs at 133 MHz out of the box. It also has horrible low power characteristics and requires quite a bit of external circuitry to get feature parity with something like an STM32. And for many applications, the offerings from ST and such would be better choices. But where the rp2040 shines is bit-banging fast protocols, the excellent SDK and support for the chip, as well as what I would say price to performance, since for just $1, or around $2 to $3 if you include the QSPI, the crystal and such, it packs quite a punch. The combination of PIO and DMA is particularly powerful, since it allows you to interact with quite fast protocols with almost zero CPU involvement. Now, the next section assumes that the viewer has a basic understanding of the PIO peripheral. If you don't, I recommend you watch these videos, links in the description, first. Don't worry if it doesn't make sense, after playing a bit with it, you'll get it. Now let's look at what I was trying to accomplish. I had a description of the protocol and the idea to stream video over USB. So first I decided to just implement the basic protocol to make sure I understand how it works. This was actually done on an STM32 a while ago, when I got the display. So here is the first tip. Before doing PIO, DMA, repeating timers, and complicated interrupt chains, first implement the basic protocol in C to make sure you understand and know how the protocol works on a deep level, so that debugging and creating PIO code later would be easier. After I confirmed that I can in fact drive the display, came the design of the overall data flow for what I wanted to accomplish. First of all, I would need to implement a frame buffer in the microcontroller's memory, to have something that can hold what I want to output. Remember, the display has no buffer and needs to be constantly fed data. Also, a frame buffer in RAM allows me to just use DMA to output the data to PIO directly in a loop, without taxing the CPU, and keep the display showing something even if the rp2040 is busy reading in data or computing a new buffer. If I wanted to stop here, it would be quite simple, but after reading in a datasheet that you can do per pixel PWM dimming in order to get brightness control, I wanted to implement it. I wanted to make the process as simple as possible for the host machine. So I decided to make a 320 by 240 by a byte array as a frame buffer, where values from 0 to 255 represent the requested brightness. You will see why this was overkill later. In order to achieve the PWM dimming, I decided to add two smaller frame buffers that are 320 by 240 bits, and an incrementing counter of the current frame. The system was intended to work as follows. After a small frame buffer is transferred, a DMA fires an interrupt. The interrupt increments the frame counter variable, changes the current frame buffer for the DMA, and asks it to do a transfer on the other buffer. This is needed because while DMA is busy putting data into PIO, the second core on the Pico constantly compares the current frame counter to the brightness value in the big frame buffer. And if the value on the buffer is above the current frame, it is turned on and stored in the smaller buffer that is currently not being outputted by DMA. In this way, the processing and output of the data is happening in parallel, but if only one buffer was used, it could cause tearing, which is why I opted for two separate buffers. Since the task of computing things was offloaded to the second core, I could just use core 0 to receive data via USB and put it into the big frame buffer. And with this, an important piece of advice arises. Use the peripherals. Microcontrollers are often built to chain, mix and match, and do all sorts of crazy things with putting peripherals together. For example, did you know that the DMA system of the rp2040 is Turing complete? In this project I used the second core to offload processing, PIO to bit bang, DMA to offload sending of data and a huge amount of RAM to store several frame buffers to improve quality. This doesn't mean that you should start instantly using all the peripherals, since that can be harder to debug, but whenever possible it is a good idea to try and use the purpose-built blocks for what they were designed. Thankfully, the Pico SDK exposes a lot of these in very convenient helper functions. With a rough understanding of how I want the overall system to operate, I began implementing the protocol in PIO. I usually start by looking at the protocol and breaking it down into simpler, repeating, predictable pieces. This display, for example, has 3 clocks and 4 data pins. The 4 data pins are all sampled in parallel when the main pixel clock, VCLK, is falling. Next, after every completed line of 320 pixels, or 80 VCLK pulses, because we transfer 4 pixels at a time, a horizontal sync pulse is issued. Similarly, after a completed frame, a vertical synchronization pulse needs to be issued, known as VS. I want to be able to just send pixel data and let PIO handle the rest of the protocol. So I need to make the PIO count how many things it has clocked out already. Because the PIO doesn't have any math instructions, I use 2 counters for VS and HS. Then the required number can just be put into the X and Y registers, and then using the jump, X and Y instructions, it is possible to decrement and jump on 0. This was accomplished by sending the values that we need to count as the first thing into PIO. Here, at startup, the state machine pulls in data from the FIFO and then copies 32 bits into the X register. However, another issue arises: resetting the registers once they hit 0. There is no choice while keeping it inside PIO other than using one of the registers as permanent storage of the value we want. This is why we copy the same value from the FIFO into the Y register too. To someone starting out with PIO, this might seem impossible, because the state machines only have 2 scratch registers and we would need 4. But this isn't actually a big problem, because it's possible to just offload the slower HS pulse into a separate state machine and just synchronize it with the main one using interrupts. This is how that looks like. Here we have the same startup and saving into X and Y as we saw in the previous state machine, and then we jump to a statement waiting for an interrupt. Now that our second state machine is waiting, let's go back to the first one and see what it's doing. Here, after setup, we jump to the start transfer bit and begin by decrementing 1 from our counter, aka the X register. If X is non-zero, we jump into the transfer part, where 4 bits from the FIFO are outputted into the GPIO and the VCLK is pulsed for the display to latch those. This repeats in a loop now. Next, when X is 0, it means that an entire line was clocked out. An interrupt is fired to let the second state machine know that a horizontal transfer was completed and that it should decrement from its current counter too. After that, the first state machine is reset, by resetting X and making an end-of-line pulse on the HS line for the display. In the meantime, the second state machine performs a loop, also decrementing its storage register, Y in this case, keeping the clock pin high until the desired number of lines has been transferred, and while resetting, a small VS pulse is performed to let the display know that an entire frame finished transferring. Surprisingly, this naive implementation worked first try and instantly saturated the display being too fast. This is when the delay cycle adjustment part came in, as can be seen from all the sprinkled delays across this code. After that came the implementation of the frame buffer subsystem. Here again, after I implemented my theoretical approach, it almost worked. The problem was that the computation of the binary buffer was too slow for the 8 millisecond frame time required for a 120 Hz refresh rate. The first thing I did is set the compiler to do maximum speed optimization. Next, I removed division and did bit shifting to speed up the calculations. But this still wasn't fast enough, so this is where I looked into just how fast you can run the rp2040. Turns out that the speed is limited by the QSPI flash, only rated for 133 MHz. But you can actually push quite a bit beyond that to about 200 MHz. Next, one can increase the core voltage and add a clock divider to the execute in place hardware, and with that, you can run pretty much every rp2040 at 400 MHz in a stable manner. I haven't seen it crash or behave weirdly in my entire testing. With this overclock, the second core was easily able to keep up with crunching the numbers. Now the last part was to get the USB protocol working. First step was to design the protocol. At this point I have decided that this display only has 3 distinct brightness values: off, half on, and fully on. This should have been obvious in hindsight, since if you want a 60 FPS refresh rate of your image, and you can only update the display at 120 Hz, you get 2 frames per one perceived 60 FPS frame. Anything more and the image will appear flickery. With this knowledge, designing a protocol for sending data was relatively easy. Calculating the bandwidth required went as follows: 320 by 240 display resolution times 2 brightness depth of 2 bits times 60 frames per second yields approximately 9 megabits per second. Looking at the USB 1.1 max throughput of the rp2040, it only has 12 megabits per second. So together with the USB overhead, this will be tight. Because of this, a binary protocol was devised, sending 4 pixels worth of information in 1 byte, 2 bits per pixel brightness value. It will be just a continuous data stream, and the only synchronization mechanism would be a timeout. I tried using the built-in printf function of the SDK to transfer the data, but that was way too slow. So I discovered that you can directly talk to the tiny USB stack if you include it in your headers. That was a lot more efficient, and I was even able to wait until the buffer had filled sufficiently to warrant draining it. I found that 2 bytes is the right size and going above has no gains. At the end of writing this, I noticed that I had enough RAM for another full frame buffer, and that without it, tearing of the image occurs. So at the end of the USB transfer, DMA quickly transfers data from the USB buffer to the actual frame buffer. DMA was a tiny bit faster than using memcopy in this case. In parallel to all of this, I was also developing an application to stream a portion of a computer screen to this thing. At first, I reused my Rust app that I made for streaming things to a VFD, but making it asynchronous was a bit of a pain, as well as adding a nice GUI, so I decided to switch to C++ for the desktop app, as well as using the wonderful imGUI library. Here, all the subtasks were put into separate threads, mutexing as required. The following threads have been separated: screenshot taking thread, compute thread to process the image and prepare for streaming, GUI thread, and finally the thread that sends out the data through USB CDC, or basically USB serial. This code is a giant mess in a single file, hacked together to just work, but if you want to look at it, it's available on my GitHub. After all of this, a frame rate of about 57 FPS was achieved, which I think is sufficient to make my point about how powerful PIO really is. Also, the occasional line artifacts you see, I think is actually the internal refresh mechanism of the display, to update the display without turning on every other pixel in a row or column, as seen in this EL display made by Applied Science. I hope you enjoyed this overview and learned something new.